Well, good morning, everybody. Welcome to Ellensburg, Washington, USA. The local time is 8:48 a.m. and we'll begin our discussion of absolute age dating at the top of the hour at 9 o'clock. So if you're watching this in replay form, go ahead and skip ahead 12 minutes to listen to the beginning of the program. But for those that are watching live, good morning to you all. It's always a thrill to have you all watching from around the world. Good morning. Looks like we're communicating okay this morning. Audio, visual, I always ask about that, Don't want to be too... Good morning, Evelyn. Belgium, good morning. It is a beautiful morning here, yes. Slight breeze, but not much, and wonderful sun. A little chilly, but good stuff. Danville, New York, good morning. Idaho, Marin. Yeah, there's a little breeze right now. And I've got my little cozy fort just for the iPhone here and a little bit of foam around the edges, so we'll see how things go that way. Jim is in Europe. Thank you for joining us this morning. Robert in Sweden, good morning. Japan, you are a regular Mr. Blue something, or Ms. Blue something. Always fun to see the exotic locations. Connell, Colette, and Ava, good morning from Portland. Hey, you kids, I'm glad you're up. Early for you guys. Did you get dragged out of bed for this? Netherlands, good morning. Another Japan, Wisconsin, UK, Kathy in Brisbane, Australia. I could go on forever reading all these, but I guess we should do a few other things. Let me have a schedule for next week. Let's look at that. I've decided that the next 5 live streams, so that's Tuesday, Wednesday, Thursday nights, and next weekend, Saturday and Sunday, will be all related to the Ice Age floods. And you're like, well, wait a minute, you've already done the Ice Age floods. You're really going to do more on the Ice Age floods? Haven't we already done it all? And the answer is no. I've got a bunch more to discuss with you. But the point is, especially after today, when we talk about determining absolute age dates from certain kinds of rocks, we will be confined to the most recent 2 million years of time, and actually most of our discussion will be in the last 25,000 years in time. So we'll be talking about some very recent geology for the next 5 lines, for the next week, basically. So I promised the schedule. Let's look at that. So if you're a regular by now, you know we don't do live streams on Monday, so I won't see you until Tuesday night. And we'll be talking about something called the Palouse Hills, which is a very unique landscape here in eastern Washington. It's related to the Ice Age. Wednesday night, talking about Glacial Lake Missoula and Lake Lewis and a few other things related to Glacial Lake Columbia. Thursday night, talking about Dry Falls again, but also going over to Palouse Falls. You know my drill, right? I'm a Washington guy, so we'll be primarily focused on specific places in eastern Washington. And then I can't believe I'm doing it, but I'm talking about climate next weekend. I'm talking about climate next Saturday in the last 2 million years, and then something I've never done, but I want to, just basically forcing myself to learn some new stuff. I have some things that I'd like to do here, and no more screwing around, let's just do it. So these Sundays are controversial, including this morning. So that's the plan. I'll I'll post that sheet on social media, and we'll get the word out a little bit. Hopefully we can get all sorts of people watching these things, you know. It doesn't just have to be, well, yeah. We still doing okay? No buffering issues? I watched some of the replay from yesterday. I haven't watched it all yet. It feels like we're doing okay, streaming-wise. Occasionally get a little clicking in the audio. You know how finicky I am with this sort of thing. But I think that's just when I'm really amped up and screaming. I mean, I can talk at this level, which I guess wouldn't be that great if I did the whole lecture in this voice, but I think the audio is so good that even with this basically whispering to you now, and it feels like it's still working. William with his boring comments. Okay, thank you, William. Great to see you this morning. What else do I have to say this morning? What else do you have to say? Yeah, there's hardly been any traffic so far this morning. You know, I usually come up on these weekend things. You know, I get up a couple hours ahead of time, and first thing I do is come out here and set up the board and start thinking about what I'm going to do with you guys, and so peaceful. But I suppose the next hour we'll have a few visitors zooming by. I've noticed a bunch of you are obsessed with that missing piece up there in the shed. Well, we used to have a beautiful big tree, a box elder tree that was mostly hollow, turned out. And it grew so big that we didn't want the shed to fall down, so we cut out a notch to allow that big tree to continue. And then we had a big windstorm, shocker, and one of the big limbs fell down and crashed onto a couple of things. This was like 15 years ago. So we took the tree down. It's kind of half dead and half hollow, and we miss it. A couple other big trees we used to have is we had a beautiful black walnut that we used to call Walter. Walter the walnut. And that was easily our favorite tree in the whole neighborhood. We were biased, of course. And it died. There's been a black walnut disease in town here. So a number of beautiful 80-year-old walnuts have been dying in the last few years. So we're in transition here with the grounds here at the Zentner estate. Just a dinky house, but anyway, we miss our big trees, but that's life. Oh well. Oh well. All right, we got 4 minutes, and I need to really concentrate for this one. So I'm going to take a full 4-minute mental reboot, and we'll get... Oh, you know what? No, I'm sorry. Thanks to Bryce and Melissa, who dropped off some cookies yesterday outside the porch. You've been watching the geology videos, and so thank you for that. And thank you to Hay Farmer Roger, who pulled up in his pickup. Liz was here, but I wasn't. And he dropped off this amazing little book/pamphlet talking about the age of the Earth when it was written in 1941. And the evidence we had back then was the Earth was 2 billion years, not 4.6 billion. It was written by George Gamow, kind of an astrophysicist. Must be part of some sort of series. A mentor book, whatever that means. But thanks, Roger. I'll get this back to you. Okay, I gotta go think for a second. Well, good morning to you all. Welcome to my backyard here in Ellensburg, Washington. My name is Nick Zentner. I teach at the college in town, and I'm happy to discuss absolute age dating in geology with you this morning. This is actually part 2 of a lecture that we started yesterday. And so I think I want to spend the first couple of minutes thinking back to what we did yesterday. And if you're watching this lecture in replay, maybe you want to pause and go back and watch live stream number 29, which is called Geologic Time, and see what we did there before you finish with this guy here, live stream number 30. You can do what you want, but that's a suggestion. Not required, but may be helpful to you. So what we're coming with a couple of the bullet points from last time. Here's our rain-soaked piece of paper from yesterday's live stream. No problem with that today. Bluebird skies. And we were going through different ways to use logic and common sense to put things in chronologic order without actually knowing how long ago those events happened. And this was one thing we did together. We took all these different geology rock layers and a couple of geologic faults and this thing, which is a big blob of prehistoric magma. And we used 3 basic laws to put these things in order. If you're a Geology 101 student, you've already been taught this. Any kind of geology class usually gets to these basic rules in a hurry because they're pretty easy rules. All right, so the idea is we put these things in order, and there's the order of the on cue, muffler boy. So going from bottom to top, we've got a sequence of events. But yesterday, when talking about relative age dating, we didn't actually know when that magma came into the picture and solidified into rock. Like, did that happen 1,000 years ago or 5,000 years ago? Did this granite form 10 million years ago or 10.2 million years ago? How in the world would you possibly know that? And that's the topic of our discussion today. So this can also work, so I just whipped this one up half an hour ago. So here's another one, just talking about relative timing. And you know what I think I'm going to say right now before I forget? To me, an important message that's often not included in talking about absolute age dating, which we're about to do, is to come back to the idea that the absolute ages determined in laboratories work beautifully with the relative age dating laws that we see on the ground, out there in the desert, with our dusty boots, and we're thirsty, and everything else. In other words, I think, and you may correct me if I'm wrong, but I think a lot of people who are not fans of the absolute age dating techniques we're about to talk about are assuming that these are dates that are just coming out of a lab with no context, with no kind of field check, essentially. And I'm here to tell you that there's beautiful field checks with the dates we're about to talk about and have them plug in here. So we're going to come back to this after we talk about the chalkboard discussion and come back and put in a few dates. But right now, what do I have here? I have a canyon wall. This is, again, trying to get us thinking from yesterday. We have 1, 2, 3, 4 rock layers. Using superposition, we do that. And then here I have actually 2 igneous dikes. In other words, places where magma squirted up through the picture. And I know that the magma squirted up through this area after layers 1 through 4 because they cut across layers 1 through 4, but we actually have two different squirts, 2 different batches of magma, maybe separated by tens of millions of years. Again, we don't know yet. We're just doing relative age dating. But is it this guy or this guy that's going to be chapter 5 in our story? And the answer is this guy. It's going to be this guy. And then 6 happened here. And you're like, well, how do you know that squirt of magma happened before that squirt of magma? And the answer is the rule of cross-cutting relations. 6 interrupts 5. 5 had to be there before 6 to come through the picture. So we'll come back to this, I think, late this morning. And maybe put a little cherry on top of our discussion. Okay, one more Of course, the cross-cutting relations, I'm still talking about relative age dating, ramping up and getting ready for today. Of course, this also works with faults. So here's our fault blocks that I've used in many of these live streams, but notice that I have a red line. Let's think of that red line now as a layer of volcanic ash that fell out of a sky for some sort of prehistoric volcanic eruption, okay? So we've got the red line. I'll do this. So this is a layer of volcanic ash. It must have a date, and we'll learn how we can determine the absolute age of that ash in just a second. But this rock layer below it had to have happened before the volcanic eruption, and this layer had to have happened after the volcanic eruption. Well, what if we do a faulting event? What if we have a big earthquake? And we take those three layers, bedrock layer, ash, and then another bedrock layer, and then we have a big earthquake on a normal fault. We know then the fault happened after those three layers were created. Okay, I feel like hopefully we're up to speed and ready to go with our discussion today. And I have one more preamble, and I promise I won't take 5 minutes on this. As I mentioned yesterday, I'm a spiritual person. I attend Mass at the Catholic Church in town many, many times a year. I don't come every week, but I come regularly. And I'm involved in the music. I'm involved in the choir, and I cantor up on the altar, leading certain hymns and parts of the Mass. It's an important part of my life. And I mention this again today to make sure that you realize that I am not part of this battle, this intense battle between science people and religious people, where there are no shades of gray between those two end members. I guess I am part, but I'm not firmly on one side. Of course, I tend to lean towards the science part. That's been my life's work. But I have sympathy, and I have a portion of my life that is spiritual. Not just Christianity, could be any religion around the world. So the last thing I'll say about this is I don't have any expectation this morning of finding some magical words using this chalkboard to convince anybody to think differently. And I've thought a fair amount about this over the last 25 years because, as I mentioned yesterday, when I talk to public groups, there's usually some folks who are, combative. They don't want to believe or hear a number that's 100 million years old. And there's an intensity to that question. And to that, it's anger. It's something's bringing that energy to that discourse. And when I was younger, I was confused by that energy, that motivation to push back. And at least from my point of view, I think I understand it more now. And the best way I can say it is, if you are on the spiritual side of things, your spirituality has been built into you from all the people that you love. Your parents helped you think spiritually. You have these patterns, these methods, these rhythms in your life that are tied around the spiritual part of you. And so it's not just you with a few ideas, it's everything that you love and everything that you know. It's your identity. And so when this science person comes and tells you that something different than what you believe with all of your heart, of course you're going to push back. It's an attack. I'm attacking your whole family, your whole community. At least that's the way I think that many folks see it. And so I suppose there'll be some comments with this lecture, and eventually months later there'll be all sorts of stuff with comments from all points of view. I don't mean to be a lightning rod. My only objective is to share with you how we know the ages of these rocks. That's it. And I have no abilities to go beyond that point. So, I feel better doing that. Let's go ahead and get started. Absolute age dating. How do we know that this rock is 812.3 million years old? That's an absolute age. That's our topic today. Okay, well, first off, it doesn't work. This process does not work with all kinds of rocks. So, let's eliminate some rocks right off the bat. Here's a beautiful limestone, and it's part of the Kaibab limestone. I collected this outside of the national park. And I collected it and brought it home, not only because it's limestone, but because it has a beautiful fossil in it. I was in the desert. I had just finished hiking the Grand Canyon outside of the national park, and I found this beautiful fossil inside of this limestone. Well, absolute age dating, the process we're going to talk about today, does not apply to sedimentary rocks, because sedimentary rocks are composed of fragments of other rocks that have been swept together and cemented together. And so if I take out one grain from a sedimentary rock and get an absolute age for that grain, I'm actually getting an absolute age for a mountain that's 4 states away, where that bedrock was eroded away, swept into this warm, shallow sea, and then accumulated into these coral reefs, et cetera, et cetera. So sedimentary rocks, sandstones, shale, coal beds, not applies to today's lecture, okay? Metamorphic rocks, I'm also going to X out. And you're like, well, hang on now. I know that you can get absolute ages out of metamorphic rocks. And you're right. But if we're doing a basic absolute age dating lecture, which we are right now, and we look at these complicated metamorphic rocks, this is metamorphic gneiss, G-N-E-I-S-S, metamorphic gneiss. There's minerals in here, but there's complicated histories with metamorphic rocks. Multiple cooling events, multiple deformation events to get these kinds of rocks. And so that's not the place to start with this discussion. So yes, you can get some absolute ages using certain techniques from metamorphic rocks, but too much for us today. Instead, we are going to be 100% focusing on igneous rocks this morning. And to me, and I think to most, that's the easiest way to communicate how we get these numbers, how we get these very, very old ages from rocks. So let me do a little bit more show and tell and show you a couple of examples of igneous rocks that we can actually get absolute ages from. Igneous rocks, you know what an igneous rock is, right? An igneous rock, I don't care what kind of igneous rock it is, it was liquid at one point. It was hot liquid. We call it magma, or lava if it's on the surface. And then if you lose the temperature of that magma, that liquid rock that's hot turns into a solid rock that's cold. And we can calculate how many years ago that happened. How many years ago, how many millions of years ago did that hot magma cool into solid rock? And the minerals that formed during that cooling process is what we're talking about. So, this is the Mount Stuart granite that we've talked about a few times. Technically, it's a granodiorite. Okay, this has been dated, age dated at 93 million years old. How do we know that? It's coming in just a second. Please be patient. I know you just wanted to start with the process, but I feel like the context is very important. So, 93 million years old, Mount Stuart granite, just north of town. Another igneous rock. Looks very different, doesn't it? This is welded tuff. This is from a supervolcano explosion, where we have this amazing cloud of ash and rock and all sorts of stuff, and then that stuff comes to rest, and it welds together, and we can somehow go into this rock and calculate or measure how many years ago it was that that magma solidified into this igneous rock. Here's another granite. It looks very different than Mount Stuart. It's got different minerals in it. This has potassium feldspar inside of it. This is from Vermont. This is a granite from the Snoqualmie Batholith up by Snoqualmie Pass in the Cascade Mountains. Same idea. Igneous has to be what we use for today's lecture. Even stuff like this, which is volcanic ash, is igneous, and we can figure out the age of this volcanic event. This is from Mount St. Helens in 1980. We didn't need to do this process because we were living here in 1980, and we scooped this up. Jim over in Ephrata scooped this up off his front yard. But we can take prehistoric volcanic eruptions that happened thousands of years ago and figure out the age. Okay? Igneous, igneous, igneous. So, you ready? You ready to talk about this process? I'm going to erase the chalkboard and try to keep the pace going the best I can. There'll be a little bit of math here, not much. A little bit of chemistry, not much. Let's do it. So, hope that you're ready to go. Hope you see what we're doing. So let's use this beautiful granite from Snoqualmie Pass. Okay, that will be our granite that we're going to try to get an age from. So what is the process? Well, step one is you go up into the mountains and you actually break off a piece of rock that looks relatively fresh. Now, some of you know that you can get rotten looking rock. It's all corroded, it's all weathered, it's all kind of ugly looking. And that's why we have these big rock hammers half the time, is we're trying to get rid of the rotten stuff and get into some good looking rock like this that has not been altered, at least visually. It doesn't look like it's been altered. It's from the inside of a granite cliff, let's say. Okay? So we collect a nice sample like this. Wonderful. So we did step one. We collected a rock. And the rock in this case is called granite. But again, you just saw some other examples. It could be rhyolite, the rock we could collect to get an age date. It could be an andesite, could be a welded tuff, could be volcanic ash. You got it. Okay. So you're aware, hopefully, that rocks are composed of different minerals. So what I'm holding is a rock, but these black and gray and white specks that you see inside of this rock are called minerals. Okay? So when we get this rock back to the lab, the first thing we do is we actually crush this rock up. We put it in a chipmunk crusher. It's got these jaws on it. You got to put your earplugs in. You're in this kind of hermetically sealed lab room. You got your white lab coat on, and you put this thing into this rock crusher, and it literally crushes the rock. And by the time we're done with this rock crushing experiment, we basically have broken all of these little minerals away from each other. We've actually crushed the rock up, and all the white minerals we're going to put in one pile. All the gray minerals we're going to physically put in another pile, and all the black minerals we're going to put in a third pile. We're going to separate the minerals physically. So, the white guys that we have separated out of this granite are feldspar. It's a mineral called feldspar. And we're going to carefully take all those white minerals and we're going to put them in the garbage can. We're not going to use them. And all the smoky gray guys inside of here is a mineral called quartz. You've heard of that. And we take all the little, this is like sawdust, we're going to take all the little gray things that are in the sawdust pile and throw the quartz away too. We're not going to use them. We're not going to use those white and gray guys because they've got the wrong chemistry to measure how much time has gone by, because we're ultimately trying to figure out what? We're trying to figure out how many years ago did that red hot magma underground cool to form this granite. That's what we're trying to figure out. How many years ago did that happen? But the little black guys in here is a mineral called biotite. And I can't use my better camera on the back because I've got my little cozy fort for the iPhone here, but maybe you can see that these black minerals are shiny. This is biotite mica. The sun's going behind the house here. And the biotite micas, these little black specks, are what we're going to measure. And so we're going to hunt through with our little forceps, our little tweezers, with this little pile of black biotite mica specks. We're going to paw through those black guys and find one that looks particularly fresh. Like if another little black speck is got a goldish, kind of tarnished look, throw it away. If it's got a torn corner, throw it away. We want a black biotite speck from the inside of this fresh granite. Okay? So now we're down to one black biotite speck out of this whole rock, and this whole rock is from an enormous mountain cliff. We're down to one little black biotite speck, and we're going to analyze the chemistry of that one little black biotite speck to get the age of when this entire magma chamber cooled off. Good morning. Okay, so we're going to send our one little black biotite speck to a laboratory that can do some analysis for us. And we're going to wait a few months, and they're going to charge us a few extra $100 probably for us to wait. And then we'll finally get our results. In that lab, running our biotite sample through a mass spectrometer, they're going to tell us, here are the elements that are inside of your black biotite speck. So suddenly now we have left the macroscopic world where we can see the black biotite speck, and now we're down to an invisible world where we're looking at elemental percentages that are measured in a mass spectrometer, but we can't see those individual elements, just like we can't see the elements in many of these substances that we live with. Now, once we get to the invisible world, a lot of people leave the discussion. I can't see it, I don't believe it. Coronavirus, can't see it, don't believe it. Carbon dioxide levels can't see it, don't believe it. So to me, that's a threshold from I was with you until you went to the invisible world. What can I do? I don't know. I can just report the science that's been done. Okay? So a list of common elements found in a black biotite speck looks something like this. You recognize most of those. They're pretty common elements. I mean, these are the same elements like on a periodic chart in a chemistry classroom. These are elements that are in food. Make sure you eat your potassium, eat your bananas, that sort of thing. Okay? So these are the common 5 elements that are found inside of a black biotite speck. And the mass spectrometer people, the people in the lab that send us the results, not only tell us the elements, but they're telling us the percentages of the elements. In other words, they've measured how much potassium, how much argon, how much aluminum, how much oxygen is inside of that black biotite speck. Now, your host has not used his space very well. Your host wanted to write 2 more columns off to the right, but it's a relatively small chalkboard compared to the chalkboards at school that I used to have. So what's this guy going to do? Yep. If you're new to us, we do live question and answer when I'm done with my portion of the program, and it's 9:24, and I hope to be done by about 9:45. But there's a few more steps to discuss, isn't there? We're doing absolute age dating methodology here. Okay, so kind of backwards. I wanted to just keep going over here, but I ran out of room. So now I'm going to keep our 5 elements, and I'm going to make a column. I'm going to make a column of percentages that these folks, I used to send my samples to Denver, so we'll just say that. So the Denver people finally ran our samples. I mean, it took months, whatever. There was a backlog of orders, I guess. And so they finally give us, here's your elemental percentages Here's your elements, and here's the percentages of your elements in your black biotite spec today. Denver says you got 15% silicon, 65% oxygen, 5% potassium, 5% argon, and 10% aluminum. Thank you. That'll be $312. And somehow we can use those numbers to determine the age of the granite. So we got a ways to go, it feels like, doesn't it? Okay? I'm going to solve this problem in just a second. And I'm going to solve the problem using these two steps. We're not going to do it right now, but if you're a student who wants to do this on your own, it's a two-step process. Once we get to this point, we're going to make a second column of percentages, and then we're going to compare the parents in both columns. But we're not ready for that. We need to take a break from our math problem here, and we need a little bit of background on radioactive decay. And I feel like anytime I use a word that's like radioactive decay or isotopes or something else, people like click off. It's Sunday. I don't want to do this. I don't know. We got more than 700 people. I'll keep my eye and see how many we lose. So we go to my little course pack. This is like day 3, by the way, usually of my geology class. And so you got some kids who add late. And so this is the first lecture they hear. It's like, what did I get myself into? I thought this was going to be like studying like dirt or something. And this guy's talking about chemistry, but they stick around. Okay, I don't want to get too bogged down on this, but we need just a little bit of background. So, elements have been discovered over the last, 200 years or something like that. We continue to add to our list of known elements. And some of those elements are radioactive. Radioactive decay was discovered. Marie Curie, back in the very late 1800s into the first part of the 20th century, she was a major scientist. And so basically this idea and this measurement and this discovery of radioactive elements that actually physically change themselves from one element to the next, was first discovered in the late 1800s. And here we are 120 years later, and we're still doing that. We have a friend. He's shy this morning. Bijou's got a dopey collar on. I guess he lost a bet. Maybe I'll show it to you if I can chase him down. Okay, so radioactive decay, first discovered in 1898, let's say, is the natural change, completely natural, from an unstable parent isotope into a stable daughter isotope. Now, this looks scary and unapproachable, but let me try my best. Certain elements do this radioactive thing. But not all elements do this thing. So silicon, oxygen, and aluminum, the elements that are in our black biotite spec, are non-radioactive, which means they don't do this, which means they're just sitting there. And if there's 15% silicon in our granite today, there's always been 15% silicon in that black biotite spec. If you're a non-radioactive element, you don't do this radioactive decay thing. But the thing that Marie and others discovered in these labs was that some elements are actually radioactive, which means, and this sounds almost impossible to believe if you're not familiar with the concept, there are some elements that naturally change themselves into a completely different element. It's like magic. Like you're born a certain way, and then over the course of your life, you are slowly changing into a completely different person. If you're a radioactive element, that's your reality. And so this verbiage here, there's just certain isotopes of elements that do this radioactive thing. And you may have heard this term parent and daughter in the case of radioactivity. Let me give you some examples before we lose our motivation completely. I don't know, maybe this will kill it. So the whiteboard today has some parent to, I'm not flipping you off, parent to daughter isotope pairs. And this isn't a human invention. This is simply humans 120 years ago discovering this in a laboratory. That if you have a certain isotope of potassium, potassium 40, it slowly, very, very slowly, gradually changes into a completely different element called argon 40. Forget about half-life for right now. Uranium-238, an isotope of uranium, naturally decays into lead-206. Carbon, you've heard of carbon dating. Same thing. There's a certain isotope of carbon, carbon-14, that naturally changes very slowly into nitrogen-14. So my first major point of this morning is this. If you find an igneous rock with a mineral that has radioactive elements inside of it, then you have this natural decay happening inside of that rock, and if we know the rate of the decay, the rate of the change, we can keep track of time. So let's just pull back for just a second and realize that without Marie Curie's discovery of radioactivity 120 years ago, we wouldn't have a way to figure out how old these rocks are. But that major discovery of radioactive elements helps us find a process to keep track of time and have some confidence that we know how many millions of years ago that certain magma cooled or that certain volcano erupted. Okay? You feel like you're still with us? Let's keep rolling. I don't want to lose our steam here. That said, isotopes, I guess you can read on your own, but isotopes, there's elements and there's different isotopes. Here's carbon with 3 different isotopes, and there's different things happening in the atoms. Let's not worry about that right now. But this is the other thing we do need to focus on, and that is, the other tricky part of this is that now that we realize we actually do have, did you catch it by the way? What's the first radioactive pair I had for you? Potassium 40 decaying into argon 40. So we chose that granite from the top of Snoqualmie Pass. It had biotite in it, and the biotite has both potassium 40 and argon 40. In other words, it's got the parent and the daughter in the rock, in that black biotite speck. And so we not only need an igneous rock, we need the certain igneous rock that's going to have some radioactive material inside of the black specks. And we have that in this example. Okay, so the other idea is half-life, and I'll try this quickly. Half-life is talking about the rate of change. Like how fast or how slow does this former stable configuration decay into this, that former unstable configuration go into a stable guy. So this is the parent going into daughter, and the way that we basically have a stopwatch to keep track of how this happens. First of all, with all of our measurements over the last 120 years in laboratories around the world, not just one lab, laboratories around the world, we are confident that this decay from parent to daughter happens at a constant rate. The rate does not change. And so if we can measure the rate of parent to daughter decay in a laboratory over a certain amount of time, and we assume that that rate does not change, then we can back calculate and realize that these half-life takes billions of years in many cases. So the half-life is the time that it takes for half of a given amount of parent to decay into the daughter. And the leftover parent, if you go through one half-life, the leftover parent then is going to split in half again. And the leftover parent will split in half again. So you never get to zero with the amount of parent isotope. You keep decaying the remaining amount of parent as you go through different half-lives. But half-life is the time it takes for half of a given amount of parent to decay into the daughter. Let's get back to our problem, solve it, and hope for the best. We'll hope that you're still with us. Okay? So, what was the way to solve the problem? Our 2 steps for success. So, Denver has given us our information. It's up to us to solve the problem. First step, make a second column of percentages for when the magma actually cooled. In other words, when the rock, when this igneous rock, when this granite actually hardened. Okay, we can do that, can't we? So here's step one. This says percentages when the rock formed. Okay, how much silicon was in the magma when the granite formed? What's the number? Correct. 15%. It's non-radioactive. It's not going to change. How much oxygen? 65. How much aluminum? 10. If you're a non-radioactive element, you don't change. You don't play this decay game, but you're not going to be helpful to us. But, as discussed, we have both the parent and the daughter isotope in this black biotite spec that Denver has sent back to us. And we know the half-life of potassium into argon is 1.3 billion years. Like if I give you 10 nuggets of potassium and I wait 1.3 billion years, and we come back and enjoy those 10 nuggets of potassium, we're going to be down to 5% potassium. We're basically going to lose half the mass. And argon's a gas, by the way, so we're actually going to have half of the potassium after 1.3 billion years change into gas and go up through the chimney. And then if we go another 1.3, the remaining amount of potassium will decay again by half. That's why it's called half-life. Okay, so how do we do this? So which is the parent? Potassium is the parent. Argon is the daughter. Potassium, parent, argon, daughter. So how much argon do you think was in this original granite? What number should we put right here? 0. Our rule is the only way for us to get daughter is to have some parent and have it decay. So if we're going to form the granite X number of years ago, we're not going to have any argon, we're not going to have any daughter in that original granite because we need the decay process to happen. So our rule is there's never any daughter in the original rock, and therefore there's going to be 10% potassium in the original rock. Is anybody still with me? I'm not going to go ahead until I can say, is anybody still with me? I feel I need to check in with you. If you're in a room with me, I can see if people are drooling at this point and it's just not working. And then I try something else by throwing things or something. Of course, gotcha, yes, good, still following. Okay, great. Thank you, thank you, thank you. Okay, so our 2 steps. We just did our first of the 2 steps. We're almost ready to solve the age of this problem, or the age of this first granite. But you'll notice that our 10 here, the amount of parent, is simply by adding our parent and daughter together to get the original amount of parent. If our rule is we never have any daughter in the original rock, then our original amount of parent is simply adding these 2 guys together. Because what is this daughter really? What is this daughter in this granite that they measured in Denver? It's decayed parent. This is 5% stuff that used to be potassium that's already decayed during the life of the granite. So to get this number, we add 5 plus 5 and we get 10, and we've done our first step. What's the second and final step to solve the problem? Compare the parents in both columns and use your logic. So potassium is the parent. By the way, we could do the same process with uranium decaying into lead. So by the way, potassium to argon, the one I'm using, is common for biotites that you find in igneous rocks. You know that I like talking about zircons lately. Zircons have a lot of uranium in them and lead. And so the zircon story is doing this uranium lead dating, and notice that the half-life is different. And these 2 radioactive pairs work on rocks that are about older than, I think the minimum age for a rock that will work with this process with these 2 guys is like 100 million years. So you can't get a volcanic ash that happened last week, or no, a volcanic ash that happened during the Ice Age and do this process. because the half-lives are too big, and you're not going to find zircons. Actually, you are, but anyway. Not worth getting into. Carbon dating, I think, is on many people's minds, and when I talk to people about this in the general public, they say, well, tell me about that carbon dating. I don't think I believe it. And they assume carbon dating is used on rocks. It's not. Carbon dating is this process that we're talking about, parent and daughter, but notice the half-life is less than 6,000 years. And so the carbon dating is used on organic material. You've got a piece of wood. We'll do this next week with the Ice Age discussions. You've got a piece of wood in a deposit. You've got some charcoal. You've got a bone. You've got things that have organic material in it, and carbon and nitrogen are in that. So you can date younger things, less than 100,000-year-old things you can date with carbon dating. Same process, but you can't use carbon dating on rocks like this, and vice versa. Okay. So comparing the parents, which is our second and final step, is comparing 10 and 5. I promise we're done with this first problem. The question is, how long does it take to go from originally 10% parent down to 5% parent today? Do you have an answer? How old is this granite that we just sent to Denver? What's half-life? Half-life is the time it takes for half of a given amount of parent to decay into the daughter. Half of a given amount of parent to decay into the daughter. I picked the easiest possible example for number 1, didn't I? I picked a granite that's age is exactly 1 half-life. The answer for our first granite is 1.3 billion years. By the way, that's not the age of the granite at Snoqualmie Pass, so you caught me there. So this first example is 1.3 billion years because we have exactly half of the given amount of parent decay into the daughter. Whether this is working or not, we're going to continue. I'm going to give you 2 more examples as quickly as I can, and then we're coming to your questions on this process, okay? Our second example, I'm going to keep everything. I'm going to collect another granite now of a different age. I'm going to keep everything the same. But this new granite that I just collected, this other granite that I just collected, which is going to have a different age, is going to have slightly different numbers for parent and daughter isotope in the black biotite spec in the granite. You with me? So with this example number 2, let's have these be our numbers that Denver sends us. Granite number 2, 7.5% parent, 2.5% daughter. What's the age of this granite? First step, make another column of percentages. Oh, shit. I mean, shoot. Sorry, kids. Okay, I had my numbers in the wrong column. This is the column of the numbers that we get from Denver. So granite number 2, 7.5% parent, 2.5% daughter. What's the age of this granite? Okay, we got to do our steps. There's never any daughter in the original rock. We add the parent and the daughter together. 10% potassium in the original rock. What's the second step? Compare the parents. Ask how long it takes to go from 10 down to 7.5. What's your answer? Have you already typed it in? What's the answer for this problem here? How old is this granite? Correct, Gord. Correct, Alex. Teresa. Got a decimal point problem, but otherwise we're doing pretty well. The answer here is 0.65 billion or 650 million. And you're like, I don't see it. How's that possible? Well, our first example, we went 10 down to 5, didn't we? And that took 1.3 billion years. But now, in this second example, we're going half the way. We're not going 10 all the way down to 5. We're going 10 just down to 7.5. And you actually need calculus and some differential equations to do this properly, but we're not going to do that. But our answer for example 2 is taking the half-life, a full half-life of potassium to argon, and cutting it in half. And 0.65 billion is the number that you get when you divide 1.3 billion in half. Maybe that works for you, maybe it doesn't. Now, if you're getting cocky and you feel like you've got this totally nailed, that's great. But let's do one more example. I got a little trick for you that might throw a couple of you off. This isn't a power play. This is just trying to communicate what we deal with granites that are older than one full half-life. So this is our last example. This is granite number 3, if you're still somehow following along with us. Switch them. And I'll wait a few minutes for this one. So this is granite 3. This is our last example, and then we'll go to your questions. I'm wondering if you can calculate the age of this rock. Oh, I'm seeing a lot of answers that are correct. I'm seeing the 2 answers that I've been giving this lecture for a long time. And we get a lot of hands up. It's the 3rd day of class. And there's usually 2 numbers that always bubble up. And I'm kind of seeing most of you are right on the mark, but a few of you are giving the other answer, which is totally logical, but not accurate in this case. Okay, the answer is 2.6 billion years. 2.6 billion years. And if you put yourself on the line there and you've got the wrong answer that you typed in, it's okay. I'm super glad that you're with us and thinking. So it's common for students to have a difference of opinion here, and they think this granite is either 2.6 billion, that's the correct answer, or 1.95 billion. So you're not alone if you typed in 1.95. Many, many students in the past in this lecture have said 1.95. But it's 2.6, and here's why. First of all, we got to do our process again, don't we? There's never any daughter in the original rock. We add these 2 guys together. We have 10% original parent once again. This time, we're going 10 all the way down to 2.5. We're going 10% parent originally all the way down to 2.5. So this has to be the oldest rock, doesn't it? Does that work for you? We've got the most radioactive decay with this last example. Therefore, we've had the most time transpire. And the trick is, I'll just do it verbally because I can't find the... Oh, here it is. The trick is 10 down to 5 takes how long? 1.3 billion years. That's a half-life. But here's the trick. To go from 5, which is the remaining amount of parent, down to 2.5, we go another whole half-life. Each time you take a given amount of parent and decay it in half, or cut it in half, that takes a full half-life. And since the half-life of this parent-to-daughter pair, potassium and argon, is 1.3 billion years, it's 1.3 billion years each time we cut the remaining amount of parent in half. So where'd the 2.6 come from? 1.3 plus 1.3. Let's just do it verbally now. Bijou, you want to say hi to these guys now? Yeah, come on. Let's say hi to these guys. I'll let you. All right, so Bijou's wondering if you're doing okay. He lost some kind of bet. I don't know what this collar's all about. I haven't quite gotten the scoop from my wife yet. But Bijou is wondering, is everything okay with you? Are you feeling like this is working for your brain? Does this somehow deviate from what you were talking about before or learning before in another class? Isn't that what you're wondering? Are you worried about these guys? Aren't you humiliated wearing this collar? What kind of clown show is this? You keep cutting the remaining amount of parent in half, and each time you do that, it's a full half-life. So what if, I'll just do it without writing it all out, what if this number was 1.25? What would be the age of the granite if this was 1.25? The answer would be 3.9, wouldn't it? We keep cutting the remaining amount of parent in half, and each time we cut that remaining amount of parent in half, it takes a full half-life. You never get to zero with the amount of parent. Isn't that right? Yeah. Okay, that's what I had planned. Oh, the last thing I wanted to do was just to back up with, oh, I see, he wants to get inside and have some, right. Hang on just a second. Come on, you're going to go and have some lunch. You're going to have some lunch. This will be short, I promise. The last thing I wanted to say is then, if you're like, okay, that seemed kind of convoluted, and again, it's just based on all these assumptions, and it's kind of these magic numbers coming from these magic labs, like, are you sure? And I would only say this. If we go back to the field relations, and we actually sampled and got an absolute age for this, and sampled and got an absolute age for this, it always works. Those absolute ages from those labs, from those rocks, always check out with the field relations. What I'm saying is, the absolute age of 5 is definitely going to be older than the absolute age of 6. There's never an exception to this. Or another important woman that we've talked about in the past. What was her name? Another Marie? That's weird. Marie Tharp instead of Marie Curie. But Marie was giving us this map of the ocean floors of the world. I'm losing my son now, but you get the idea. And you remember that in the 1950s, researchers were going back and forth across the Atlantic Ocean and sending instruments down and collecting basalts on the ocean floor. Every spot. Go down, collect a basalt, get an absolute age, get a basalt, absolute age, etc., etc. And after all of that absolute age dating, realized that the basalt was brand new at the mid-ocean ridges and got progressively older in both directions away from the mid-Atlantic ridge. My point is that this is a beautiful field check with all of this stuff. And we'll see with the Ice Age floods, same idea. Even surface exposure dating of boulders using radioactive decay. It checks out with the field work. If you're a good scientist, a good field scientist, you don't take all these numbers and just believe them. You have to make sure you put them in contact with these field relations and they check out. In other words, they make sense with the field relations and the relative age dating laws that we've had for a long time. Okay. That was a long one. It's almost 10 o'clock. I have no idea what you're going to be asking right now, so I'm curious. If you've already typed in your question with uppercase, I'll scroll back to it. If you want to ask some right now, I'll try to scroll around best I can. Bijou is just hungry, that's all, so he's in enjoying his lunch. We have an automatic feeder, and so 10 o'clock, he's programmed mentally now to do this. I'm going to bring you closer to me so I can stay in the sun. Okay. Get in the right scroll bar and don't let go. What element has the longest half-life? Leland, I don't know off the top of my head. But I don't think I've seen half-lives bigger than this, so maybe my answer is uranium-238, which is a very reliable dating technique with the zircon crystals these days. And there's error bars on these dates, depending on which lab and which techniques. And I've never been in a lab, a mass spectrometer lab, so I don't know the messy details of running the samples and getting accuracies. Scrolling. Where did the original aging numbers come from? Carol? What I have, I guess I have cat hairs all over my, right, okay. So these numbers were observed. In other words, you can, let's say from 1895 to 1920, there were all these measurements of which elements were doing this decay. And these high precision, tiny amounts of radioactive decay in grams that are hovering every year. And then again, if you assume a constant rate, what we do, a constant rate of this radioactive decay, you can then do some pretty basic math to figure out how many billions of years or millions of years or thousands of years to go through this one half-life thing. But those numbers are all coming from laboratories in the early part of the 20th century, 100 years ago. And if there had been some fault finding, if someone found a bunch of faults with those measurements, that would have been developed recently. But those measurements were so beautifully done that we still use that 120 years later. I'm on the right scroll. I'm on the right scroll. Here we go. What is the decaying process among rhyolite, dolomite, aragonite, and calcite? What is the decaying process? Owen, I don't know how to answer your question, except to say that we know the few elements that do the radioactive decay, and they do the radioactive decay in a very organized way. And so calcite, for instance, doesn't have the right elements. Many minerals don't have the right elements to keep track of time. So I'm not sure why you picked those particular rocks. We have skateboarders at 10 o'clock this morning. Does potassium ever totally decay into argon, or is it there always a trace? Well, we never get to zero, so we never totally get run out of our parent material because of the way the decay works, but also because of the incredible amounts of time that we're talking about. Our Earth is 4.6 billion years, so obviously we're not even going through one of these with many of these radioactive decay, radioactive parent-daughter pairs, and yet we can keep track of time even though we don't go through one half-life because of this constant rate process. Thank you for the questions. Does argon-40 exist naturally in the Earth? There are some complexities here. Thank you, Larry. Where did that go? There. Sorry, Danny. Yes, I have been corrected, which is totally fine, by geochronologists. If you're really into this absolute age date, you study geochronology, keeping track of time in geology. And there is some argon-40 that apparently is natural, meaning it's not the result of this change. So that's a teaching choice, just to make it as simple as possible and say there isn't any daughter in the original rock. Apparently there is some of that, and they somehow, and I don't know the answer, can separate out the daughter that's from decay and the argon that's not from decay. So it's a good point. I've always meant to learn how to get into the weeds there, and I haven't. Can granite be manufactured to determine original elements? I mean by utilizing some lava, or does it take too long, if this makes sense? VK, can granite be manufactured to determine original elements? I think I see what you're asking. There's a guy named Bowen, I forget his first name, but he's famous for the Bowen's reaction series, where he was doing all sorts of simulations of magmas in laboratories. I think he was like 100 years ago, the 1920s or 30s. Somebody can probably add his name now. But he was doing experimental work, and synthesizing different magmas of different chemistries and figuring out the certain temperatures that different minerals formed, and knowing that quartz comes in last in a cooling granite, for instance. So I'll just take the spirit of that question, and there's been plenty of that kind of experimental work with how magmas cool. Evelyn, age 7, how do you separate the elements in your lab after it's been crushed? It seems like it would look like sand. Good question, Evelyn. In our lab, and this is only my part of the process, was crushing up the rock and separating out the minerals. So you could do that, Evelyn. You could just take this and crush it up, and you're right, you would have like sand. You'd have black sand and gray sand and white sand, and just separate those sand piles out. But the element thing is different. All this stuff on the chalkboard, all the stuff in the chalkboard, Evelyn, is in one of those little black guys. It's all happening teeny tiny inside of one little black speck. That's the thing we're sending. We're sending one little black speck to Denver, by the way. We're not sending the whole rock. So in that case, yes, I don't know how to go through, separate out those elements, and that's what a mass spectrometer does. I mean, I don't know the details there. Thank you for the question, Evelyn. How many blocks from this house do you live? Not to get too, actually, well. Assume start with 100% potassium-40. Are there any other isotopes of potassium? Larry, there are other isotopes of potassium. I don't know them off the top of my head. And we're into the details now of how the geochronologist can tease out the radioactive pair and ignore the other isotopes that are not helpful. And I don't know how they do that. There might be a lot of that with this live Q&A. Since I don't know the details of the lab work, I may not be able to help. I'll be as honest as I can. In your example, does the argon remain bound in the rock, or is it just missing, being gas? It's always been fascinating to me that you're measuring argon, which is a gas, inside of a mineral millions of years after the granite cooled. Like, why would there be any gas left? But I've been assured that you can get that gas, and it's only if you go to a crazy high temperature that the gas kind of bleats out of the rock. Again, I don't know what I'm talking about right now. But I'll take your point. At least with uranium and lead, or rubidium and strontium, or some of these others, what is it, like silicon into aluminum and oxygen, at least with many of those you've got solids. But you're changing phase. Our potassium argon is not only going from parent into argon, but we're going from solid into gas. It's truly bizarre stuff. Does argon and nitrogen not occur naturally, or is it created only through half-life? The way I'm teaching it, those isotopes of argon and nitrogen are the result of the decay, Melanie. But we're back to that comment that if you really know your stuff, chemistry-wise, there is some of that argon and nitrogen, even of that isotope that's not from the decay. And I don't know how they tease that out. What's the oldest rock you've handled? Oh, you know, in this rock that, in this book that Roger loaned me yesterday, written in 1941, and their message was the age of the Earth was 2 billion, not 4.6, but 2 billion years in 1941. This is written by a guy who's, up on the latest science. Somewhere in here, he's talking about the oldest rocks known, and they were either in Finland or in Canada, I think. And the main reason we've pushed our age of the Earth back to 4.6 billion is we keep finding these rocks that are older and older. And the oldest rock that I'm aware of is in Australia. But you're asking about me. Oh, I don't know, just I guess some Precambrian rock. I guess some rock in Glacier Park that's maybe at 1.2 billion, part of the Belt Supergroup in that supercontinent lecture. Can Dike 6 have been contaminated when going through Dike 5? Contamination is a problem, Donald. in general, especially if you have kind of blobs, like you have granites and then another granite. But I'm distinguishing here because these are igneous dikes, which are usually tabular. They're usually following some sort of fracture system, and they're just, think of this as a crack, not a fault, but a crack that's opening up, and then this magma is shooting through very quickly. And it seems logical to me, no, it's extremely common to have one dike cut across another dike totally cleanly. Like this wasn't a Monday and this was a Tuesday. You know, there's tens of millions of years often between these two events. So to have a quick ascent through a fracture, it's common not to have assimilation of this pre-existing rock in this stuff. But I'll take your point. There are situations where you have this contamination. I mean, there's plenty of problems. So some of your sample collection is part of your job as a field geologist. You don't want to go into a place where things have been mixed, or there's other reasons that your sample is going to suck. You want to sample correctly so that you can get the most accurate date. 7 billion year old material dated in Australia, January this year. Please demystify, question mark. Santos Kumar, are you the guy from the Himalayas? You've been joining us almost every morning. It's great to have you with us. What country are you from? I have not heard of 7 billion year old material dated in Australia of January of this year. So that's news to me. Wish I could help. Can you use Paleo Magnetism and spreading center rate of spread and calculate rock age right? Well, PM, that's kind of what I was trying to get at. I probably, if I do this kind of lecture for real for the public, this is the first time I've done this kind of talk for the public. I've always done it in my classroom, but you know, I'm kind of venturing out into the real world, shall we say. And so I feel like I'm going to be changing this quite a fair amount. I probably won't go through all these details next time, and I think I'll hit these field checks or this connection with real field relations harder, because to me that feels better, to put your hands on these relationships in the field and then have it be backed up with these crazy numbers. But the question from PM was paleomagnetism. We know about changes in magnetism in the geologic past. I'll go back to the Atlantic Ocean floor. Something also I haven't taught, but everybody wants to ask about paleomagnetism. It's a weakness of mine, but I can bone up on it. Yes, we know the ages of the Atlantic Ocean floor get older and older from absolute age dating of minerals and basalts from Iceland out to Scotland and Nova Scotia, let's say. But there's also magnetic minerals in those basalts that show us the polarity switching, that we have normal polarity and reverse polarity, and this magnetic field of the Earth going back and forth. So I view it that the absolute age dating of the rocks helped us understand this crazy flipping of the magnetic fields through time. I don't think of it the other way, which I think is what you're saying. Can you use paleomagnetism to calculate the rock age? I can't think fast enough to see how that would work, but maybe you're onto something. Sorry. Does cooling time affect the mineral content? Does cooling time? I don't think so, Titus. That, again, because of Bowen's, was it Norman Bowen? Because of Bowen's work, again, he was creating these magmas in a laboratory setting and then playing with chemistries and cooling the temperature of the magma and seeing these different common rock-forming minerals crystallizing at particular time windows, temperature windows. And so what was your question? Does the cooling time? I don't think the rate of cooling is that at all. I think it's a temperature thing, as I understand it. With a cooling magma or a cooling lava flow, it's a temperature thing, not a cooling rate, a thing that controls which minerals are formed. If quartz is not used for radioactive decay dating, how is it used in cosmogenic dating? Well, that's an interesting question. This is from the Carlson family. Let's hold off on that. We are going to talk about getting dates during the Ice Age floods of these boulders brought in on ice rafts. This is next week. and measuring how much radioactive decay there's been on the surface of a boulder, and we are using the mineral quartz. And the Carlson family is saying, you're not using quartz here. And off the top of my head, Ryan, I'll have to look into it, but I think the radioactive pairs in the quartz for cosmogenic dating is, the half-life is too young for what we're doing here. But I need to look into that. And I will. Is there a sensitivity to the argon test? How accurate can they be today? I don't know the methodology, Denise. I'm sorry. How does radioactivity work? I've described the decay process, but if you're asking about the mechanics of that, that's more of a chemistry and physics question, and I don't have the background. I'm sorry. We're already at 10:10. I'm going to just do a few more of these questions. I wish I had time to answer all these. I'm going to scroll all the way down to the bottom. Oh, so another one asking about, can residence time in the magma chamber influence the silica content? I don't think so. What's an analogy? Like, you make different kinds of dough? You make different kinds of dough. You're playing with different ingredients, and you're making pizza dough or something. I don't know, pizza crust dough. And so you got these 3 batches of different kinds of dough, of different ingredients. I mean, that's the chemistry difference between those things. And then you put them in the oven. I don't think it matters how long you bake that dough. It's the chemistry that's controlling what's inside of the pizza crust, not how fast or how slow you bake the crust. You can see that I'm not a good debater. I'm not a particularly quick thinker. You've already figured that out if you've watched me try. I'm like trying to read the words. But once I can take the time to think through things, at least from my brain, I feel like it's a satisfying way to teach. But this is a weakness of mine and kind of scary for me to try to answer questions about chemistry and physics and radioactive decay with my limited background. What are these rocks doing for all these billions of years? Standing still? Are they in motion? Well, Michael, I'll take your question and try to answer it this way. This is what this last thing we'll do. So there's radioactivity happening right now in this rock. It's a natural process. This business of decay from a parent to a daughter isotope. We didn't make radioactivity. We didn't start it with a gun going off or something like that. As long as the Earth has been around, we assume that radioactivity has been happening with certain elements at a constant rate, and therefore working with those precious few elements that have the ability to radioactively decay, they allow us to keep track of time. And they've unlocked this amazing ability to figure out the age of rocks. Now, I hope to teach for another 25 years. I'm not saying that I'm going to, but I enjoy this so much, I'm hoping to be teaching in some form to some audience until I'm in my mid-80s, God willing. And so 25 years from now, will there be some adjustments to this? Will there be a slightly new technique used? Is it possible somebody will come along and prove that this is all baloney? Doesn't seem likely, but you know the history of science, don't you? To stand here on this beautiful Sunday morning and say, that's it, we have figured it all out. We have unlocked this secret process that's been going on for billions of years, and here we are in present day, and we've solved it. We know it doesn't work that way. We continue to make discoveries, many of them minor, some of them major. And that's an exciting thing to look forward to. And so I'll finish with this. Yesterday, I pointed out that my first Geology 101 textbook in 1984 had the Earth at 3.6 billion years old. And in 1941, the leading idea is the Earth was 2 billion years old. So who's to say that this textbook, probably won't be a textbook, but some textbook I hold up in the year 2042, is it still going to have 4.6 billion? Is it still going to be talking about zircons and carbon dating? Or will there be a new discovery to help us even be more accurate than we are now? And those folks in 2042 can look back at us here in 2020 and go, wow, they did their best, but they weren't as accurate as we are now. And I'm optimistic that we're heading in that direction because we've made tremendous progress since then. A toast to you. Thank you for joining us for this session and all of these sessions. I think this is number 30. The first of these live streams was on March 17th, and it's been a blast, and we're still going week by week, but I have next week figured out. Ice Age floods the entire week. A discussion of the Ice Age the entire week. The next time I'll see you will be Tuesday at 6 p.m. Pacific time. The Palouse Hills over by Pullman, Washington and Moscow, Idaho. A really favorite landscape for many of us. I've got some things to say about the development of that loess and those hills. Ice Age lakes, Glacial Lake Missoula, Lake Lewis, Glacial Lake Columbia, and what we know about the absolute age layers in some of those slackwater sediments. Ice Age waterfalls, dry falls, of course, in northern Washington, but also Palouse Falls, back over by Pullman. And some details about where the water went at certain times and what we know about coulees being carved at particular times, using relative and absolute age dating laws, you see? And then next weekend, back to a more global audience, at least that's my assumption, that on the weekends we catch people live that don't normally catch us during the week because of time zone differences. Good Lord, I don't know what I'm going to do here, especially Sunday, but I got a week to figure something out. And we can have a spirited debate there. And if you had very specific, pointed, and thought-provoking questions this morning, I'm sorry I didn't get to it. I will enjoy reading your question in the replay. So, from the Berggrens and the, can't remember your name, Beckharts, we got cookies that have been delivered to the house and coffee. Here's to you and your health. Here's to the health of your loved ones and your friends and the people that live in your community that are working hard on your behalf and our behalf. And we'll just keep rolling with this holding pattern. Cheers. Delicious. Thanks again for joining us this morning. Enjoy the rest of your Sunday and your Monday and your Tuesday, and I'll see you Tuesday night at 6 p.m. Pacific time. See you next time. I love you. Morning. Embarrassing. Goodbye.